Thank you for the invitation. It's an interesting symposium. And my talk is about a numerical simulation of debris flow, and to talk about material behavior, and in particular, to talk about a constitutive model, right? And I just start. Right? So we know what kind of debris flow it is. So I got this picture on the right-hand side. You could say here, usually debris flow starts with a slope failure, right? And that runs down slope and turning into a kind of debris flow. And we call it the run-out. And after some distance, and come to a gentle slope, and then we come to deposition. So this is the whole process. So usually in the beginning is a slope failure. So it's the domain of solid mechanics, where the material is treated as a solid. We know this. It's the domain of solid mechanics. The run-out analysis is in the domain of fluid mechanics, right? So I just mark this. I'm going to talk about this because we know too well about slope failure. So I don't have to talk about it. This is kind of a classical topic in solid mechanics. Then come to the deposition. I will just leave it out now, right? On the way downwards, and you could say it might impact against obstacles, and this is why the symposium here, right? And interaction between the debris flow and check dams, we got here obstacles. And finally, the deposition. You know that, you see now the geomaterial or debris material on the way has changed from the solid to fluid and back to the solid again, right? So, so this is a very important and very difficult topic for us. So well beyond our classical scope of soil mechanics. And there is something I want to also tell you, debris flow need a kind of a charging time. So this means that after debris flow happens in an area, it needs some time until some material deposited on the slope. So you may have another major debris flow. So some of the characteristics which are very important for us is first the phase surface. The second thing, which is less well known, is the extremely low stress level, right? Because we have debris flow with a depth about a few meters, 1 or 2 or 3 meters. And if you calculate the self weight, you come to a stress which is about 10 or 20 or 30 kilopascals. And this is very low in soil mechanics. So I have a look at what kind of material we have. And now we need to have a look at debris flow in the whole broad spectrum. So I have to make some, how can I say, we have confine ourselves, limit ourselves to specific debris materials. I'm not talking about mud flow or something else, so with a large percentage refined material. Or we don't talk about a rock avalanche with a very coarse and dry material. Somewhere in the middle, very broad, and we talk about the debris material. So this mainly consists of sand and gravel and some of the stones, and that makes about 90% of the material. About less than 10% is our fines. So in soil mechanics, we call it fines, and this means the clay and silt. Well, that's interesting. You have a look at the literature of geohazard, you'll find lots of descriptions of the poorly sorted material, right? And that is, if you are used to soil mechanics, is our well-graded material. You see now, kind of one man's meat is another one's poison, right? For us, it's the well-graded material good as engineering construction material, but for debris flow is called poorly sorted. So whenever you see poorly sorted, it's well-graded in soil mechanics. So most times we deal with the water-rich, water-laden water-rich, and dense granular flow. It is very important to notice dense granular flow. So this means on the way downwards, we see friction, we see collision among the particles. Sometimes the friction dominating, and other times it's collision dominating, right? And how can we handle this part of fines, right? This is usually treated as a part of the fluid, right? Because they're suspended during the flow process. So I mean, this 10% fines and clay and silts, and they are added to the water, and that is treated as viscous fluid. And one of the things how we do it here is to have a look whether a particle can be added to the fluid or as part of the solid. Is when you have a look at how fast it settles, right, compared with the flowing process. Because when the settling process is much longer than that, and you look at as part of the fluid. So this means the debris material is a kind of granular material. Mainly consists of sand and gravel. A few stones are usually sorted out, just like in your test, they probably don't consider big stones. Right? So I got a picture from Wikipedia, and you may have a good idea what kind of how this material looks like. Right? And the picture here shows you where it is, where a certain fraction of soil is added to the viscous regime, or it is going to come to the fluid or come to the solid particles. And now how to handle this, I don't want to talk about a numerical because we have two students who took part in your predictions using SPH. So basically, all these numerical methods have something in common. That it starts with the field equations. We call it sometimes balance equations, mainly balance of mass and balance of momentum. So I just put it here, and important to say this is the stress for the solid, the stress tensor for the fluid. And here we've got the body forces and accelerations, and we can further the fluid stress can be further separated into the usually what we have for water, or you've got a viscous stress, so the stress tensor could be anisotropic. So that we just put it here, right? This is well-known results. And now once we got this equation, it can be solved together with a kind of constitutive model. And there are a number of numerical methods. And if you look at really the practice in numerical simulation of debris flows, which is important in hazard estimation in a practice. Most of them are based on so-called depth average model, because that simplifies the equation further. And that is mainly based on the theory of shallow water proposed by Savage and Hutter, which is very well known. So most of the models, numerical tools, are based on this. So I list on the left-hand side, you can see some of the very well-known numerical tools in different countries, and starting from down in Canada, that is by Professor Hanger, and and another program, RAMS from Switzerland, developed by SWL, and in France and Japan. So most of them are based on this method. So the solution is based most of the time on finite difference, with some of the refinement. And you see now finite difference and finite volume. And recently, the so-called point-based continuum model has become very popular. So among them, so the lattice Boltzmann, SPH, NPM, and so on. I'm not talking about this because if you have been working in geotechnical engineering for a while, you know that these are numerical tools and they come and go, very much like finite element. So we know that once finite element was very in fashion, so many papers about that in application in soil mechanics and geotechnical engineering. And today, nobody talks about that. Why? Well, this has become a standard tool, right? So finally, what is very important is certainly the physics. What is the physics? You see now the field equations are the same for all disciplines, right? So what makes the difference is the constitutive equation, the material behavior. Now we see we got two stresses, basically the solid stress and fluid stress. So they are the total stresses. And now, if I look at constitutive model, treating solid and fluid as an entity, and we'll end up with these models, which is very widely used. And the computer code I'm talking about, right? And they all use this one of the three models, or even all of them. So starting from Bingham model, yes, that is in the 1916 proposed by Bingham. And the other two models are kind of German models, Fürme in 1955 and Herschel-Barclay in 1922, right? So we don't have to look at the details, but one thing is sure, we can say now, they just express the total stress as a function of the strain rate. So very much based on fluid mechanics models. So the simplest model in this case is, of course, the Newtonian fluid. So they're all based on Newtonian fluid, stress as a function of the strain rate. Yeah, we don't have to look at the details, and usually they include the further yielding stress here, right? So this means of treating the granular material not really as the fluid, because the fluid will flow at a very small stress, no matter how small, how low the stress is. But we know that debris flow does not do that way. So we need to put an initial stress to start the flow. So this initial stress is the yield stress. All right. And there are some refined models that's put here, for example, the so-called quadratic models. That include a further term. Later we talk about this term. It's very interesting. It's very much based on the observations. So a linear one and the quadratic model, right? And then it basically expresses the shear stress as a part of the friction plus the viscous. The first is friction, the second is viscous, and the third is so-called dispersive stress, right? It may have different microscopic origins. You may have this kind of quadratic dependence for dry granular flow, but you may have also this quadratic dependence for a submerged flow, right? Good. These are things we know. And let's have a comment. I want to comment in this slide. So this is the state of art of a practice, right? Not only of a practice, I would say almost 100% in the research. So what are the deficits of this model? First of all, it's a kind of single phase model. It does make a difference whether it's water or sand, gravel, on things. They look at it as just like a single phase. And I would like to recall similar analysis in geotechnical engineering. We call it total stress analysis. It's just before Terzaghi proposed the principle of effective stress. But even today, you have a look at in the practice, and the kind of single phase is still used. You think about total stress analysis, undrained analysis with undrained strength. It is still very popular. I mean, existence of such model has certainly its justifications, right? And they make use the constant model, usually the so-called rheological model, expressing the stress as a function of the strain rate, right? And that is fluid. Right? And we say granular material is certainly not fluid. Why? And we know that such material during the flow will exhibit some kind of normal stress effects. So what is it? So normal stress effect is something very new or something extraordinary in fluids. But it's very common for soil mechanics. This means when you have imagine you got a shearing in one direction, you may develop, you have a kind of normal stress perpendicular to it, right? Yeah, we simply got it. If you got a dilatancy and you got normal stress perpendicular to the shear direction, but this is very unusual for fluid. But such models do not show this normal stress effect. And as a consequence, it has no dilatancy, right? So we always say later dilatancy is very important, right? They do not consider poor water pressure. I mean, excessive poor water pressure. Sometimes it's called out of balance water pressure, but in soil mechanics, we call it excessive poor water pressure. This is part of the pressure just above the hydrostatic pressure, and which is very important for the mobility of the debris material, right? And it considers, of course, the steady motion. We say the model just do it that way. This means that model considers, if you look at the laboratory, we consider that the shear, simple shear, and a constant strain rate. It is funny, right? If you look at it in the literature, usually they are not in tensor forms. But if you look at your numerical implementation, you will need the constant model in tensor forms. They simply don't do it. Just write it as a shear stress and shear strain. That's the way how you work on it. But that is not correct, sure. And the last one, they are very, very old. Yeah, I told you the first one is 1916 and so on. So such is the state of the art, right? And now I just turn to have a look at a more recent one, the model that has gained popularity in the last few years. And this model is called so-called GDR-MIDI model. So it's a fancy name from a French colleague. French colleagues like fancy names. And just have a look at the dry case, and then develop also the case when the granular material is saturated. So guys who are working on it basically are from physics. So the physicists, they are not engineers, right? So this model is sometimes also called so-called mu-I model. I put it here. So you just consider a simple shear. The picture is this from their paper. There are serious papers, right? I don't need to put it here because all these equations and these figures, as well as all of this, are from their paper. They've got quite a lot of papers. So maybe one of the first papers is called the GDR-MIDI. So what is it in French is so-called research group of diverse materials. It's called a research group in Marseille, in France, right? And one of the colleagues there and it's called a Poulican. So he is the leading person there. They made a lot of publications. Among them in 2006, one of the publications in Nature, right? Well cited. So what is this model about? I just put here in really in a very, very short form. So they consider basically here tau as the shear stress, a function of the normal pressure, right? Tau is the normal pressure you see here. Right? And then the shear stress and the normal stress are proportional. And you would say, fantastic, this is not really new. So molar cooling is just like this. Wait a moment, there is something new, right? And they see that this proportional factor, in our case, would be the friction angle tangent phi, right? But here it's different, and they call it mu I. That's why sometimes this model is called the mu I model, right? And mu is the kind of coefficient, friction coefficient. But they say that the friction coefficient depends on I, right? What is I? I is defined here, right? It's called kind of inertial number. We'll later have a look at what kind of number it is. So let's have a look at this. Is basically the strain rate, diameter of the particles. And here in the denominator, you will see in square root, we got a pressure divided by the density of the particles, right? So if you put all these things, you check the dimension, you will easily find out that this number is dimensionless. So for a given pressure, for the given material parameters, this number is nothing but the strain rate, basically the strain rate. It tells you that the shear stress is proportional to the normal pressure, but then it's dependent on the strain rate, right? And later, and we have a look at the picture here down, and the specific expression here, it shows that the friction coefficient increases with the strain rate, right? Or the friction angle increases with the strain rate. This is something we usually don't consider in soil mechanics, right? The second thing here is phi, which is not a friction angle, is so-called a solid fraction, right? It's kind of related to our void ratio. It's the other way around, you know, the inverse of a void ratio, more or less. So the kind of percentage of the solid divided by the total volume, right? You will see that, this picture shows here, and this is kind of a linear interpolation. You will see now here, the solid fraction, this decreases with the speed. So what does that mean? If the shear speed increases and the solid fraction will decrease. Well, that is also easy to understand, right? We call it dilation. This means when with a very high speed and the material dilate, and as a consequence, and the density will reduce or the void ratio will increase. So that's everything, right? So there are quite a lot of publications here. And I think why people like it. So we sometimes, it's very simple, right? And it's not giving tensor forms, and later was further developing tensor forms. And later we'll have a look at how can we reproduce with our model the kind of results, because this is kind of material behavior that is observed in kind of testing. We'll have a look at that. So, and this mu I model brings some improvements with it. So the first one is the normal stress effect. You will see that because you're doing shearing, you may have a kind of normal stress along with the shearing. And you got the latency, which is kind of rate dependence. And you got a friction, which is also rate dependence. And they differ very much from the model before. But there is a but, and I put it here, there is a big but, right? The big but is here, it's a still rheological model. This means it expresses the stress as a function of the strain rate. It is only for fast granular flow, right? And it does not account for the initiation. I mean, if you look at here, every debris flow starts with a landslide, and that is solid mechanics. This means if the speed is very, very low, close to zero, you cannot use it. And this model cannot be used for the reverse loading, right? Sometimes you got granular flow, got to stop and go, and certainly can't use this, right? And so I spent some time on the kind of state of art, and it might be now it is interesting now to have a look at how the reality looks like, how a real granular flow looks like. So I call it a kind of reality check. So the reality check is the granular flow is not steady. It's usually non-uniform flow with very strong segregation, in particular when it travels long distance, right? And with such kind of phenomena, we call it levee formation. You would say that the coarse material on both sides, yeah, and also very coarse front. So the larger material is on the front. And in this front, and the material has very low excessive pore water pressure, right? The water pressure starts a little bit further back, yeah. So behind this coarse front, you have finer material with very high water content, saturated more or less, right? So, and now we further observe kind of unsteady flow. So this picture again from these guys from France, so GDR, MIDI, so they call it, you see definitely the formation of roll waves. So under this flow, we've got it characterized by surges and roll waves and etc. So these are very often observed in the real debris flow, right? And sometimes, and we observe also in particular when the depth is a little bit higher, we observe kind of a plug flow. And that is a part kind of, we call it localized deformation, just because the deformation is localized near the bed, right? Close to the bed. And whereas the major part of the debris flow just rides on it. So which gives rise such a velocity profile, which is very well known. All these things are not handled by our numerical model. This means our debris flow is very much unsteady. The steady, so-called uniform flow, what we handle in our model is anything but exception, right? This is something we assume, but in the real case, it is even very difficult to produce it in the laboratory, just like in a model test. We really want to have a uniform steady flow. That is almost close to impossible, right? And what's the way out of it? And I believe, right? And we got here our kind of, we got to experience, we got to know-how in geotechnical engineering, soil mechanics. If we want to handle this issue, one of the possibilities might be here to, instead of the total formulation, right? You see now, I just showed you total formulation with stress. And it's very important now to consider incremental formulation, right? We use it in soil mechanics the whole time, just because the material behavior is elastoplastic. So you just cannot use the total stress formulation. Now you turn to the kind of incremental formulation. That is quite straightforward. I don't have to repeat the details. It's basically, you see this equation is very similar to the equation before. So you need to consider kind of increments and take the rate form you can have divided by the time increment, and you easily get this rate form. You see now just simply replace the stress with the rates, right? The stress rate for the solid, for the fluid, and so on, right? And if you look at this equation, the solution is also very formula. You could use basically also the same tools I just showed you before. But what differs from the approach before is just because of this rate, you will need certainly the constitutive equation for the incremental for the stress rates. So that's the difference. And now I just want to have a look at two aspects of the whole thing. The first is, what do we know about here, the material behavior? Because at the very first point you want to do, the starting point when you want to work on a model, you want to see how's the material behavior. We know quite a lot about the soil. We know very little about the debris material. And we have a look at it. There are some facts, right? The facts check. And our model should be able in the position to reproduce this facts or observations. But in general, I just put here in the next line, I could put it as summarize of the material behavior, what it is. You just consider here maybe a stress as a kind of function of the strain rate. I put the stress and the strain rate. You know, the debris flow community will probably use tau and a gamma dot, but later you will see that it's better to use the stress tensor. So you put this kind of a stress tensor in relationship to the strain rate. And we may have a kind of a zeroth order and the first order and towards the second order. What do I mean? I mean the frictional. This is our soil mechanics, solid mechanics regime, where we know that it's rate independent. So therefore you got a zeroth order, right? The next one is the transitional range. For the first order, this is basically Newtonian fluid. It's a typical example of the first order such a model. And if the speed further increases, and we move into the inertial regime where the relationship is quadratic second order. So it's basically in general to see what we know about it. You got a model here, the model should reproduce kind of this material behavior. And on the left-hand side, you've got a frictional solid behavior, solid-like behavior. And you've got the right-hand side, you've got fluid-like behavior. In between, you've got a translation, right? The model should be able to reproduce this. And then we have a look. So this is what we know. We have a look at specific kind of observations, documentations, what we have from the literature. The next one will be what kind of challenges such observation pose to the constitutive model, right? This are the 2 points I want to handle. In order to do this, we have a look at this picture, which is a kind of one of the, I always say, the milestones in the research of the granular flow, right? It's given by a colleague in the UK, is Keynote. A legendary person. He, as a soldier, he took part in the Second World War and was in the desert to fight the Germans, right? And he was not a kind of a soldier on the front. He's more like kind of an engineer. As such, he got a lot of time. And with the time in the desert, he thought how this kind of blown sand and the desert dunes are formed. We know that we got a singing sand, right? And sliding down a slope, and you hear something, they make the sand make music. And that is what his interest was. And he published a book in 1941, and this is a very legendary book. It's called The Physics of Blown Sand and Desert Dunes, right? Very well known. So I got a copy of this book, very well written. So that's really the first research on fast flow of granular material. It's also for the desert research. It is just one of the pioneer work. And later, back to the UK, he continued his research. And one of his papers published in the Royal Society in the UK is about granular flow. It's kind of granular flow in water, right? And once you start with testing the material in the laboratory, we'll find out how difficult it is. In soil mechanics, we got quite a lot of testing devices at hand in our laboratory, and you need to go to your laboratory, your university, your Professor Ng House, an excellent laboratory, and there we got different testing devices. And then you come to the fast granular flow, you will find it's very difficult because this basically the material flows, and the gravitation makes a big problem. This means when it flows, and you will reduce the flow speed, and the particle will settle to the bottom, right? It doesn't work that way. So in order to get rid of this problem, so Keynote use a kind of fluid and then use the particles, which is neutrally buoyant. This means it's with the same density as water. So that is achieved by mixing lead with wax, right? So wax is lighter than water and lead is heavier. So you've got the right proportion. You may have the particles, you put it under water, any place, and it remains there. So that's a pretty good material. So kind of model material. And with this, he's constructed this kind of shearing device consisting of 2 cylinders. The material is in the middle. So to rotate these 2 cylinders relatively to each other, so we could generate kind of shear flow. And this is kind of where before it was used in fluid mechanics. Read the fluid dynamics, and we see that. So this is a kind of a Taylor's experiment. It's kind of very often used to study the stability of fluid. And he used this device and do 2 things. One of the things, he changed the density of the particles, right? Change the particles, and the next thing is to change the fluid, the shear velocity, right? And then he put that here in the stress, right? Stress over his number, he called it Keynote number. Again, this number, if all the things, just like the material behavior and the density are unknown, it's nothing but the shear rate, right? So basically, you could understand that the stress over the shear rate. And there is something very interesting. So on the left-hand side, the normal stress, on the right-hand side, of the shear stress, right? And we have a look at this relationship. This is more or less a kind of bilinear relationship with a point, kind of breaking point here, somewhere here, right? And at a lower strain rate, you have a linear relationship. So that's reminding us of a Newtonian fluid. As the speed gets higher, and that's how I think the kind of order changes from the first order all the way towards the second order, right? So this is the quadratic dependence. So that is kind of very well known. This is the milestone. However, later, some people reproduced the result with a similar device, and they find out that backnote made a mistake, right? You know that we do the laboratory test, we might overlook something, right? So the end, this is the ends, how the friction of the ends are considered, right? If you consider this end, the dependence is perhaps not exactly quadratic, it's part to the order of 1.5. So anyway, so you have to change from the linear kind of Newtonian fluid towards something higher order, right? I don't know, some people said you get the tendency to believe that the quadratic order is the thing you're looking for, right? We know that we work either with the testing or with the theory, we have all the tendency to look for things we want to see, right? And we see that we got a hammer in your hand, everybody looks like a nail, right? And this is perhaps the reason for it. But anyway, so this is important. Of course, these lines are dependent on the solid fraction and the solid volume fraction, that how the density of the material here is very important. The first one we know, right? So, and interesting is, and later, I don't show the results here, there was a big community of the so-called kinetic theory, right? This basically from the kind of Boltzmann consideration. You consider the points at the kind of granular material as basically virtually very large like the molecules in Boltzmann, and considering they collide and are flying around, and they're interesting, and you find also this quadratic dependence, of course, and the granular material considered there is very much dilute, so it's not kind of dense granular material, right? We consider dense granular material, and now you see the difficulties you're faced if we want to reproduce these test results in the laboratory, right? One of the way out of it might be do such a test in the space shuttle, right? And probably one day we could do the test in the space shuttle, and then you don't have a problem with the gravitation, right? This might be kind of the topic for the next proposal, right? I think that one of the professors, and probably the professor, I knows him as Professor Stein Stewart from Colorado. He did have a kind of this proposal with NASA. He did some tests there. Okay, anyway, you could look for some help. One of the major, the good help is the DM, right? With the help of DM, you can switch on, switch off the gravitation. I just show some results here. And on the left-hand side, we've got a dry granular material. On the right-hand side, suspension, basically with the fluid, right? And with different, very different volume fractions we see here. Mu is the volume fractions. So the y-axis, you would say, is the shear stress, and the x-axis, the shear rate, right? So what I want to show you, just we don't have to look at the details, but you see this kind of change, right? From the first order towards the second order, when you increase the strain rate from low one to the high one. I don't mean you increase the shear rate only slightly. So we talk about the order of magnitudes. You have to look at this, the x-axis, right? So 1, 2, 3, 4, 5. So we go through 5 orders of magnitudes, and you can observe such a dependence, right? And it is observed both in the suspension, right, as well as in dry granular material, right? Very important. Good. So what are the alternatives to test granular material in the laboratory, to test debris flow material in the laboratory? We know that the rheological model is the dominating one, right? This means people want to try to reproduce this whole thing. So the conventional route would be to use some small scale testing. You could use the large scale testing, which is a drum, right? Rotating drum. And we have in our university kind of a testing device of 2.5 meters. And there is another still big one, twice as large in Berkeley, in California, right? So the thing here is when you rotate, so you put granular material here. The good thing here is with this drum, you could observe the debris flow or kind of small scale debris flow at the same spot. So it's much easier to do the instrumentation and to do observations because you just have this debris flow that in front of your eyes the whole time, right? And that differs from the chute, what you use, right? You have to follow this chute, but here, you know, the debris flow is just right here. And then if you have a look at these results, right? The strain rate over a large kind of spectrum, several orders of magnitude. And you do see also the solid fractions, again, in a very large range, from very dilute flow to dense flow. I must say the dense flow is more relevant for granular materials. And then people working in fluid mechanics tends to introduce some numbers, right? And this comes from the partial differential equations, or you got a partial differential equations. You want to make it dimensionless, right? So that it's valid for all kinds of problems. And then you start with such numbers. So these numbers can be derived. The best well-known number is the Reynolds number. So we don't consider this. And to have a look at whether it's laminar flow or turbulent flow, that's the Guy Reynolds. The first test was carried out in Manchester, in the UK, and we've got the Freud numbers. So we don't have this. Two numbers which are relevant for the granular flow are the Backnum numbers. We just talk about that, and the Savage numbers. What are they, right? These are just compared to stresses to say which one is more important, is dominating, right? So for example, the Backnum number compares the collision stress, right? The particles may collide with each other. That gives rise to a stress. This part of stress compared to the viscous stress, because the fluid has got a viscous. Even you have a water, which has got a zero viscosity. And by the presence of particles in water, you have a kind of viscosity. And this is well known, right? The first paper about that, so the kind of epoch-making paper about that is from Einstein, right? In the wonder year, he published 4 papers. Each of paper might have got a Nobel Prize. One of them is about Brownian motion. So it's basically these kind of things. And he got something which is very much relevant for this, the viscous stress. So and he got here this number. All these numbers are dimensionless, right? The Savage number, which is also very important, it compares the inertial force, right? The inertial force with the external load. For example, in the simple shear, the normal stress, right? You see here, right? P here, the denominator is the stress, right? Where we have the Backnum number, you got a viscosity in the denominator. You put these two numbers, many people use this diagram. So I just got this diagram for these guys. They got this big drum in California, in Berkeley, in particular, Professor Dietrich, right? And that's a paper published 2 years ago, or 3-4 years ago. So they studied kind of granular flow in the big drum, and they just here to say where our drum are. Not only the drum test, right? Because small drum experiment, large drum experiment. This small drum experiment, I think, is from our university. And then they look at the natural debris flows as well, right? And you say in which regime you are, whether you're in the kind of more viscous flow, right? Matrix or less viscous matrix, and so on, whether you're in the kind of frictional or you're towards an inertial regime. And I sometimes had a look at our testing and numerical calculation of the two guys who made a prediction with your testing data. I think your data is somewhere here, make a dot. So not very exactly, but you see where you are, right? Basically very, very fast flow, right? So this is the technique people use to do that. And now you will say, I have shown you everything, right? Not very much. This is what we know about material behavior. If we want something new, I will say, sorry, we don't have it. Well, if one of you here in the audience, you have made the predictions here for Professor Ng's challenge, right? The quest and the blind date, I will say this blind prediction is very much like blind date. You want to impress the mate there and you want to show you the best side of it, but you don't know what kind of person he or she is, right? So entering into the blind date, you may have realized there are very little information available, right? A friction angle, 15-degree, grain distribution curve. And we say, is this everything? Yes, I will tell you, I'm sorry, this is everything I could give you, right? So such is the very fact. And that put a lot of challenges for the constitution model, what I'm going to talk about, right? So unlike soil mechanics, there is very little known for the debris material, very little. So when you take examples, for example, the things we usually know in soil mechanics, we take it for granted that such things are simply there, available from laboratory. They are not. For example, density, right? So this is the ABC, the fundamentals of the material behavior. Even this is difficult. The grain distribution, right? You may have it, but I can tell you, okay, this is at the beginning, at the starting, right behind the gate. Once you lift the gate, the material slides down and deposits finally there. You find a quite different grain distribution, right? In different parts of the debris body. In the friction angle doesn't help you either, right? Let's have a look at the density. Once the material is in motion, the density is very different, right? The density with the material with the dilate, with flying around. So your density doesn't tell me anything. I could tell you a range depending on the speed. And you see now it is why it is important to have this kind of mu-I model. Everything depends on the speed. Everything depends on the speed. the density, the friction angle. Even the grain distribution curve, you need to consider segregation, and that is not guaranteed. So that is very, very difficult. I told you that, and usually we add this kind of fines to the water that gives rise to the viscous fluid, right? Water and fines, and this gives rise to the fact, leads to the fact that our fluid stress will no longer be isotropic. In water, we got isotropic, from the principle of effective stress of Terzaghi. We know that part of water pressure is isotropic. P is everywhere equal, right? We got rather complex interaction between the solid and fluid, right? When a solid particle moves relative to fluid, you got a drag force, right? Usually we put this kind of drag force in the field equation there. And we got a segregation as a consequence, the levee formation, the layering, we got instabilities, right? Very, very high challenges. How can we do this? And I told you, we'll go back to the very point. I think the way out of this problem, out of the dilemma, or we want to have a model that does not only give you the result you will see now, just like the prediction, but you want to have to be more closer to the reality, to the physics. And I think here the incremental formulation will be the way to go, right? From there, you will need a concept model in rate form, incremental form. And here's how we do it. I put in this slide, really in this single slide, the most important thing here. Usually the most important thing is the simplest, right? Very much like the principle effective stress. That's very simple. If I tell you, we say, wow, that's trivial. No, it's not trivial. The first one was centered, very much Columbus, take the egg and put it on the desk. Not easy. Let's have a look. So we just assume the stress and the stress rate can be decomposed into two parts, right? I just put it red and blue. So this one of the part is rate independent part. You could call it inviscous part. The other is the viscous part, right? So this is the way how we assume. It applies for the stress, it applies for the stress rate as well. Because you take the time derivative, you got exactly this relationship, right? And the next one, which is very important, only the separation, decomposition doesn't help you. We further assume that each stress on its own. What does that mean? This means if we got a constant equation for this rate independent part, it works only with rate independent stress, right? The other viscous, you work only with your viscous stress. So these two things are decoupled. How are they coupled? They're coupled only through the equilibrium. You see now that the total stress is the sum of the rate independent and rate dependent stress. So basically from the equilibrium, right? This is the only point where the two stresses are coupled. Otherwise, you work with your model, with your stress, not the total stress, right? So for the rate independent part, we could take the hypoplastic model. We have been working on that for many years, which is very good for granular material, for large deformation with critical state and so on. We still need something for the rheological model, for the rate dependent. And you will say, come on, stop. You said you don't want a rheological model. Yes, I do want it, but now in a rate form, right? In the rate form. You see the rheological model express the stress as a function of the strain rate, but I need a function of the stress rate as something. And probably already, you may guess something that I will need to take the time derivative, right? So this separation of the stress is of course not really very new because basically Terzaghi's effective stress principle is such approach, right? The total stress is the total stress of effective stress and per water pressure. Remember, our constitutive model is only for the effective stress, right? Not for the water pressure. So here exactly the case. For the water pressure, we will just take the hydrostatic pressure or the excessive per water pressure. And this is usually we get from the boundary conditions, right? Or as part of material behavior. You got over consolidated soil, you got a kind of negative per water pressure, but that's something else, right? And let's have a look. And this is well known, we know it for this one, but we still need something. And you see now we need to take a time derivative to get a stress rate, right? And before we go that, I just want to have a look at what is our hypoplastic model here in one slide, really in a nutshell, hypoplasticity. So it's a kind of tensor relationship, right? And if you want to consider kind of a critical state, and you multiply here with a function, which is a function of the Ward ratio, And here we got a critical Wald ratio with the minimum Wald ratio, right? So you will see here, this relationship is nothing but a linear interpolation between those two Wald ratios, right? And from there, we could have that whether it is larger than 1 or smaller than 1. So this gives rise to basically the situation, a granular material which is denser than critical or looser than critical. You got 4 material parameters, and then a further parameter is A, and you could really simulate the behavior pretty well and show you here some structure tests, numerical tests with different initial densities. And you see, I'm sorry, here it's in German, I'm sorry here, but you see here the volume ratio, right? And you see this is very similar in German, also the volume string and the actual string there. German and English, they're very similar, right? So you see here the Wald ratio, independent of the initial Wald ratio, they all approach the critical Wald ratio. And that is the volumetric string, and you see all the stress strain curve finally and merge to our residual strength. So this is very interesting because that we can use really here for the frictional behavior. This is good for a very large string, right? And I put it again here. The stress should be here, all replaced by our sigma h, basically read independent part, right? Good. So this part, and we need to have a look at rate dependent part. And here we've got quite a lot of model to rely on. So I just put a list of the model in fluid mechanics, which is very well known. The first, of course, is the Newtonian fluid, and there are the Reiner-Rivlin fluid, and the Maxwell, there are fluid with relaxation, odoroid fluid. So quite different formulations, right? So some of even express the stress rate as a function of the strain rate. But let's have a look at this Newtonian fluid. I want to really start from the very simple one, the simplest one. I want to take this one and turn it into the stress rate. And you can see here, we could take the time derivative, right? On the left-hand side, we got the stress rate, which we need in our incremental formulation. On the right-hand side, this is already stress rate. If you take the time derivative, what do you have? You have the acceleration, we call it. We call it here, a kind of acceleration strain, right? The higher order. And there is something funny, interesting, I will show you here. You might not expect. Basically, this is the Newtonian fluid. I want to have a rate. I just take the time derivative to get its second expression. This is the same, right? Exactly the same relationship. And it gives you really the same behavior, the same kind of stress strain curve, because you can prove this easily. If I integrate this equation, I get back to the original kind of Newtonian fluid. But it makes a big difference when you do the numerical simulations. I put in there on the right-hand side is the kind of Newtonian fluid, right? It is the relationship between a stress and a strain rate, linear relationship, right? And that is our eta. So basically tangent this angle is our eta, which is the viscosity, right? And it shows you that if you give me a strain rate, I can tell you a stress. So basically, this means usually what we consider is the shearing with a constant strain rate, right? With a constant strain rate, you got the same stress, right? So if I got a shear stress over a shear strain, so it's very much like this. If you got a time differentiation, you got this relationship, what happens here? You will see now, this relationship tells you if this is a steady shearing with zero acceleration, and we got a zero stress increment. So this relationship will virtually vanish identically if you consider shearing without acceleration with zero. So this means we consider a kind of a steady shear. It doesn't tell you anything. You see, yeah, is this you want what you want? Yes, I want is something here. We all consider kind of a test with a constant shear strain or shear velocity in the laboratory as given. It is not, right? How can you get there? I mean, I just tell you, you drive the car from one place to the other with a speed of 50 kilometers per hour, right? And this is what we learn in physics, right? In school, but nobody tells you, in order to get a 50, you need first to accelerate because your car in the garage, right? It started and accelerate. This constant model accounts for the stress in the acceleration stage. Afterwards, you can forget it, right? You see here, I just put it here, the acceleration over the time, right? And in this, when you start it, you got the acceleration. And I can make use of the model to give a stress increment. Afterwards, the acceleration will be zero. You get this stress strain relationship very much like here. Compare left to the right. So very important to have this acceleration stage. But what happens if the shearing comes to a standstill? You stop it. You cannot stop it just now. You need to decelerate until speed is 0. And later we have a look at this whole thing. It really brings something very, very interesting. You get a quite different perspective to this. All right, after we talk about it, we can say usually, and this viscous part, we can write it kind of as a function of the stress, the strain rate, and the acceleration, right? I can choose the expression. I can, to do this, I can look for some possible expressions with the help of the representation theorems. If you look at continuum mechanics, you know, if you tensor functions, you consider only polynomials, and there you have some candidates, and here's our choice. So there is no kind of big theory, kind of microscopic considerations. Only the thing here, you won't have a normal stress effect. So it means during the shearing, you should have normal stress. And this is a possible expression. So others also possible. So these parameters at 1, 2, 3, they are the viscosity parameters, right? And you need to have a kind of dimension check, left, right-hand side, in order to find kind of this dimension. I take eta 1 example. For example, it has the dimension of Pascal times s second to the order 3, right? So these are later with some manipulations. You could say you can show they depend, the 3 parameters depend on the solid volume fraction of the granular fluid, right? It depends on the frictional coefficient, basically the friction angle. It depends on the viscosity of the fluid. All right, with all this, now I could put together to get compound constitutive model, right? And you will see here. And now, in order to show you that you work only with the stress, right? With this kind of stress, and the other viscous part, which is stress independent. I didn't include the stress just because fluid behavior, the behavior of fluid usually is independent of the stress level, right? So we got this concept model, then we can proceed to assume the parameters to do some simulations, right? And this model gives you the behavior from the frictional all the way to the inertial behavior. This means from the 0th order over the 1st order to the 2nd order. And it gives you also a kind of phase transition from solid to fluid and back from fluid to solid in a natural way, right? Just imagine increase the shear velocity, and then this frictional stress will decrease and that stress will increase. And why? Because, you know, if the external load remains unchanged, and then you should have such behavior. And now it is the last one is still the intergranular stress. This means what we consider here is the kind of effective stress of the granular material. I just show you some performance of the model. Here is the shear stress over the strain rate, right? Compared with the things in the literature with different solid fractions. And it works pretty well for the shear stress. And the right figure shows you the normal stress over the shear rate pretty well, right? And now the next one, this is in a simple shear, right? And the next picture is also interesting to show what happens in a simple shear, right? So first we have the frictional behavior in soil mechanics, and then afterwards we increase the speed, and the speed of the increase, so we got a transition point. So the blue line is the total stress, and the yellow line is our dynamic stress, the viscous stress, right? And this red line is our frictional stress. So you see the frictional stress for increasing shear strain rate, you will see that the frictional stress decreases to a very low level, whereas the viscous stress increases. So basically you have a kind of natural transition from the solid towards the fluid. And later we will show you what happens if I stop, reverse loading, and then it turns to the solid-like behavior back again. And you will see here the shear stress, and that will say the normal stress, right? And this picture shows you what we have for a mu-I model and from DM calculation, from backnote, and that is the decrease of the solid fraction with the flow speed, with the shear speed, or we call it the inertial number. The other one is the increase of the friction coefficient, right? The mu with the shear rate. You will say that the concept model reproduces this behavior pretty well. So these are a DM simulation with different kind of gravitation numbers. So it's basically how far the gravity is switched on and off. You see here we got a pretty well reproduced. And the next one is, the model, the relative model cannot be used for the reversal. What happened for the reversal? And this is an interesting picture, whereas the left is for the shear stress and the right for the normal stress. We see we're starting from here, right? So this is shearing to here, and now we want to have a reversal. So this is what happens with the reversal, right? You need to, in order to stop the shearing, we need first to decelerate. Just like, imagine you run in 100-meter dash. Yeah, right. If you want to stop, you need first to decelerate to come to a still, right, standstill, and then go back to accelerate. That's exactly what happens. So this is the decelerating phase, right? And then that is stop, right? And here acceleration in the reversal direction. And you see what happens with our quasi-static stress. You see here, right? This is with our quasi-static with frictional stress, right? And you will see that it decreases first, and then increases dramatically, and back to in the other direction, it decreases again, right? And in a quite different trend is a viscous stress. It increases with the speed, with the shear rate, and then decreases virtually to zero when you come to the standstill, right? And it increases again. So that is a very, very interesting thing. And we put that whole thing in SPH and simulate this kind of very long slope, right? And sliding down, and you could see here how it is for different angles, right? For the slope of the 26 to 30 degrees. And we have a look at here with Z, right? It's normalized with the depth, and have a look at what kind of stress we have, right? And you see here, we got a total stress, right? And here we got H is viscous stress, H is the inviscous stress, and V is viscous stress. And what you see here is if the inviscous stress or frictional stress is higher and the viscous stress is lower, and later for higher speed, right? And the frictional stress is very low, and then you could see here the viscous stress is pretty very high. So you got basically this phase transition that really happens naturally. And finally, I come to a kind of byproduct. Do I have still a couple of minutes, Professor N? 5 minutes?
Yes, go ahead, please.
All right. Yeah, great. So now I'm done. And we are now, what we are doing now, right? We are now kind of rewrite the computer model, right? SPH model to use incremental formulation. And then we'll put this consistent model in a computer code to see how it behaves, right? How the performance is. But before this basically already everything, but I will want to show you also kind of byproduct. If your consistent model includes kind of acceleration, what happens here, right? With a different stress formulation, each constant model uses its own stress, right? Only they come together through the equilibrium condition, right? What it is. Now, I want to have a look at creep, right? We know that a creep is very important for us, for softer soil, for rock, for everything. And for softer soil here is for this, everything, I mean, the stability check, in particular for slopes, right? So have a look at kind of softer soil. You got to hit a creep string over the time here. We got 3 stages. We know we got a primary creep stage. We got secondary. Yeah, we got sometimes we got a tertiary creep and towards rupture. That's what we have, right? So what exactly happens in a creep? So this constitution model, we gave you kind of, we let you look at creep testing from the very completely new perspective viewpoint. So let's have a look at how the string rate works. And this is very well known in soil mechanics. So basically the primary, so how can we get a kind of creep? You first load the sample, right, with a constant string rate. And somewhere you want to, I want to start with a creep test, right? So this means the load we kept constant. And in order to get there, you need first to decelerate, right? You see here, decelerate. And finally, we come to acceleration equals 0. So it's basically our kind of a secondary, right? And if you got a tertiary, you don't, sometimes you got a tertiary rupture, sometimes not, right? Depending very much on the stress level. And then the deformation starts to accelerate again with the acceleration larger than 0. So the turning point here is, of course, is equals 0. And we got a constant model, right, with the acceleration. And it gives you a tool in the hand because we can naturally here study this kind of behavior. And this is what I show you and how we can reproduce the material behavior and the testing results in the laboratory. And this is kind of for a soil, frozen soil, right? And we know it's dependent on the temperature, therefore you see the -10°. And the testing here in the diagram above, we see the actual string over time. And here, during the same testing, same simulations, the actual string rate over time, right? You see at the lower stress level, the string rate reduces virtually close to 0. So you don't have the kind of creep rupture. But if the stress level is higher, you start to have this kind of rupture phase, right? And then that is the string over the time. But what is interesting is it produces this creep behavior all the way to failure pretty well, right? But let's have a look at what happens inside. We know that creep means that the load remains unchanged. This means also the stress remains unchanged. Nothing happens there. Because we have this stress decomposition, we got two stresses. Each concentrated model works its own stress. Only through the equilibrium they come together. You have a look at the stress rate, like on the left-hand side, and the right-hand side, I've got a stress. Interesting thing here is, even during this creep test, the two stresses are not constant. Yeah, they do change. The thing here is, in order that the stress rate becomes 0, so if you got here blue and green, so one of them is the kind of rate independent, the other is rate dependent. If you see, if the rate independent part reduces, rate dependent will decrease, right? So the sum of these two must be equal to 0. So if you see everywhere, right? That is for the stress rate, and that is for the stress. So it's pretty interesting, right? So we hope to really to get some interesting insights, to get some interesting insights into the complexity of the debris flow with the help of this incremental formulation, with the help of the new constitutive model, right? So, and yeah, I come to an end. So what are the challenges ahead? So you work with debris flow, like your very large project, and it's a multi-million dollar project, US dollar project, and there are many issues which are not yet considered, or I mean, the tools I just showed you for different countries, what is used in the practice. So we do not, all these models do not consider so-called granular temperature. So the granular temperature, this means how the granules, the sand particles are agitated in the material. They do consider. So most of the models do not consider segregation within continuum, right? There are some very interesting work here. So, you know, you could reproduce the segregation with DM. This is what we do in the drum. You know, we did a drum test, and we did also some couple tests with DM and so on. But that's a kind of a play in a desk play. You could do it with numerical scales, but how to do that, to put this whole thing in a practice. So if you look at it in a practice, I don't think that a DM will have any chance to produce, you know, simply the large number of particles, the complexity, you just cannot do that with DM. So we need a kind of continuum description of the segregation. If we want to get there, we need to consider segregation. We do not consider it yet. We have some ideas there. And then how can we reproduce the unsteady flow, the surge and the raw waves there, right? And then how can we consider localized deformation if you got a kind of very massive debris flow, and probably you will have a plug flow, right? And with a very thin layer near the bed, and with most of the debris material just riding on it. Yeah. And the large stones, which is not considered, but here I think the DM might be very useful because you can really model the large stones with it. We know that from the force measurement in our university, got a field testing. The large stones, and while they do have a very large impact on the forces, we got obstacles there, and so on and so forth. I think this is very interesting area as worth studying, worth investigation. I think here we need also to get a perspective. As I told you, that debris flow community is very much focused on the fluid behavior, right? Fluid mechanics. And we are from geotechnical engineering, we bring quite a different perspective there, right? Because we are from solid mechanics. I think it's the combination of both that finally, hopefully, will bring us the breakthrough here. Okay, I would like to thank you very much. And that last slide is thank you. I think it's now 3-4 o'clock here in Vienna. Afterwards, I will pillow, sleep. And thank you for your attention. That goes very slow. And this online presentation, I would like to be there in person. Thank you very much. You see the upper half, the lower half, I don't see. I'm honored to share my research at your virtual academic conference. Thank you very much.